Assalamualaikum warahmatullahi wabarakatuh. My name is Sitahan binti Ismail. My metric number is 21091142. Okay, today I will be presenting about the introduction of our project on the integration of renewable energy source in power system. Okay, this presentation we cover the introduction, background and problem statement which form the foundation of our topic. As you can see the slide here. Okay, for the slide number 2 is about what is the integration of renewable energy. Okay, you can see here at this slide. Let's begin by understanding what we mean by integration of renewable energy. Okay, it refers to process of connecting energy like sources like solar, wind, hydro and geothermal into national power grid. Okay, these energy sources are naturally renewable and environmentally friendly, but they are also variable depending on weather, time of day and seasons. Okay, next is to ensure a stable electricity supply, we must balance energy productions and consumption at all times, even when renewable source fluctuate. This is where technologies like smart grid, battery energy store and advanced control system play a major role. Okay, the last is the goal is simple, to deliver clean energy reliably and efficiently to users across the grid. Okay, for the next slide is about introduction and importance of integrations. In recent years, there been a global effort to move away from fossil fuel and embrace renewable energy due to climate crisis and rising emissions. Sources like solar and wind are clean and sustainable, but as I mentioned, they are intermittent. That means the amount of the electricity they produce changes depending on natural conditions. Because of this, it's not enough to just install renewable energy system. We must also make sure they can integrate it efficiently into the existing grid so the power delivery remains smooth and uninterrupted. This makes integration a key step towards building a low carbon, recently energy future. Okay, for the next slide is about background and historical milestones. Let's take a brief look at how renewable energy has evolved historically. Okay, long before electricity, humans used wine to salt ships and water to power mills. However, during the Industrial Revolutions, fossil fuel became a dominant energy source due to their higher energy density and reliability. Despite this, renewable technologies keep developing. Here are some key milestones. Okay, the first one is about the hydro fuel cell was invented in 1830s. And the second one is the first solar cell was created in 1883. Windmill technology improved in the 1890s. And the last one is the first hydroelectric plant was built in 1882, followed by the geothermal plants in 1921. If we look at the data source in figure 1.2, it shows how electricity generation in the US has shifted over time from coal dominance to the risk of natural gas and renewable, which by 2021 had overtaken coal and nuclear. Okay, this illustrated how renewable energy has become increasingly important in modern power systems. Okay, for the last slide is about problem statement. They also have 3 problem statement that I already add in this slide. Okay, although renewable energy has many benefits, integrating it into the power system comes with significant challenges. The first one is the technical challenge. Solar and wind energy are unpredictable, and this variability can cause imbalance in the grid, leading to instability or even blackout. Okay, the second one is about there is the infrastructure challenge. Our power grid were originally designed for the central fossil fuel plants, not for distributed renewable source like rooftop solar or remote wind farm. Adapting the grid require major technological upgrade and investments. The third one is we face regulatory and market challenges. Many energy market and policy were developed with fossil fuel in mind. They don't provide flexi pricing models or incentives that support renewable energy growth. So, if we want to truly benefit from renewable, we need holistic solutions, not only in terms of technology and infrastructure, but also in our policy and planning framework. Okay, for the introduction is from this slide. To conclude my part of my presentation covering the definition, important background and challenges of renewable energy integrations. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Sabrina Metinggabrode and my metric number is 221091129. So today I'll be presenting our comprehensive methodology for assessing the integration of renewable energy sources into modern power systems. As we move toward cleaner energy, the challenges for grid stability and protection have become more complex. So let me walk you through our methodology flowchart here for assessing renewable integration in power grids and shows each step of our process from problem identification to actionable recommendation. Next, we begin with a thorough literature review to understand the main challenges. First, conduct a systematic review of recent research to identify key challenges in renewable energy integration, including reduced fault current levels due to inverter-based sources, then bidirectional power flow from distributed generation, then protection, miscoordination, and inflexibility of traditional relays. The last one is impact of inverter-based resources on system behavior and protection. The second is identify gaps in current protection strategies for renewable-dominated grids. Next is system configuration. To address these issues, we built a realistic microgrid model using MATLAB or Simulink. Our model included solar photovoltaic sources, wind turbines modeled as inverter-based, permanent magnet synchronous generator, and battery storage to manage load variation. We also included constant impedance loads to simulate residential and industrial demands, and both conventional and adaptive digital relays for protection. Transmission lines were modeled into IEEE test data to ensure accuracy. This setup allowed us to closely mimic the behavior of modern grids with high renewable penetration. The third, simulation and analysis. We run simulation under a variety of scenarios: normal operation with variable renewable output, short circuit faults at strategic locations, load changes due to the solar and wind intermittency, and transition between islanded and grid-connected modes. We analyze key outputs such as voltage profiles, current waveform, relay setting times, and breaker operation. This helps us evaluate how well the protection schemes perform under the unique conditions created by renewable energy sources, especially low fault currents and bidirectional flows. This is what we get from our research. Then, our analysis revealed significant weaknesses in traditional protection system. So to overcome this, we propose several enhancements, which is directional relays for accurate fault currents direction detection, adaptive relay settings to adjust protection in real time, AI-aided forecast-based logic for protective grid instability management, then integration of advanced energy storage and smart grid technologies for stability and reliability. The last one is validation and recommendation. We validate our findings with real-world examples, including a modern grid with distributed energy resources and the 2.1 gigawatt floating PV system in Semangan, Korea. This case study highlighted the practical challenges of large-scale renewable integration, such as grounding and insulation in floating solar plants. Based on our result, we developed actionable recommendations for improving protection and grid stability in renewable-dominated systems. Our stepwise methodology ensures a structured, comprehensive approach to addressing the challenges of modern power systems.
Assalamualaikum everyone. My name is Nur Alia Shakira binti Samsul ID and my metric number is 2210911115. Today I will presenting on power system protection in renewable energy system, specifically focusing on the challenges and protection solution in power system with high renewable energy penetration. This presentation is part of result and discussion. The world is moving rapidly toward cleaner energy sources such as solar and wind. Why? This transition supports sustainability and climate goals. It also brings major challenges to power system protection. Renewable energy, especially inverter-based sources, behave very differently from traditional synchronous generator. As a result, protection systems originally designed for stable and predictable conditions may misoperate or fail in high RES environment. So, this presentation explores both the problem and the technical solution. So we go to A, challenges of high RES penetration. The first result we observe is the set of challenges caused by high level of RES integration. First, which is intermittency. Solar and wind output is weather dependent, which causes voltage and frequency to fluctuate unpredictably. Second, fault rider truth. Inverters are designed to stay connected during disturbance, but despite the fault signal from relay. Third, low fault current. Inverter output is limited, only about 1.1 to 1.5 per unit, too low for conventional relays to detect. Lastly, bidirectional power flow, which is with rooftop PV and DER, currents flow in both directions, which confuse traditional non-directional relays. This challenge have been reported in Malaysian case study showing real impact and protection coordination. This table summarizes the key challenges and their impact on the protection system. For example, in Selangor, a rooftop PV system failed to trip during a line-to-ground fault because the inverter's fault current was too low. Similarly, fault right truth extend fault duration, delaying relay operation. This case show that the protection system must adapt to RES behavior. Next, we go to result B, which is protection issue overhead observed. From these challenges, 4 main protection issues have been consistently observed. First, blinding of protection. The fault current is too low to activate the relay. Second, fault stripping, RES variability like shading mimic fault signal, causing unnecessary disconnection. Third is islanding detection failure, when RES continues to energize a disconnected part of the grid, posing safety risk. And lastly, inadequate fault detection speed, which is inverter delay cause lower relay response. This issue has serious implications on safety, equipment, lifespan, and overall reliability. So this summary table highlights how each issue is caused, its effect, and real-world example. It also suggests suitable protection methods such as differential relay, AI classification, hybrid islanding detection, and PMU-based wire area monitoring. These strategies are necessary to fix the gap between RES operation and conventional protection. So to address these issues, several advanced solutions have been proposed. First is adaptive protection, which is change relay setting based on real-time system condition. And second, communication-based protection like IEC SID1850 GHOST enable relays to coordinate instantly. Third, inverter-based coordination allows smart inverter to play a role in protection. And fourth is a wide area monitoring system using PMU give synchronous data across the grid. And lastly, with AI-based algorithm, predict fault before they occur, reducing fault strip. And together, this approach makes protection more intelligent, fast, and accurate. So in Malaysia, these solutions are already in use. For example, adaptive relay help detect fault that were previously missed in rooftop PV system. Second, communication-based protection clear fault in millisecond in battery-based microgrid. And lastly, is a smart building with IoT use AI to prevent fault stripping due to cloud shading. This example show the effectiveness of upgrading protection system in real application. So, in summary, renewable energy bring new behavior to the grid, like low fault current, reverse flow, and voltage instability that traditional protection cannot handle. To move forward, we need to smarter protection systems that are adaptive, communicative, and predictive. Without this, the safety and reliability of the power grid cannot be guaranteed in a future powered by renewable energy. So, that's all from me. Thank you.
And for the conclusion, this project highlighted in challenges of integrating renewable energy into power systems and the limitation of conventional protection methods. Through simulation and analysis, we identify key issues like intermittency and low fault currents and propose adaptive protection and AI-based solution to enhance reliability. While some limitations exist, the findings emphasize the need for smarter, flexible protection system to support a sustainable energy future. Thank you. That's all for me.